Let's say that there are 6 parallel surfaces. This is medium 1, this is medium 2, this is medium 3, this is medium 4, this is medium 5, and this is medium 6. A light ray is incident on medium 1 at an angle theta 1. Okay. Now you are asked to find the angle of this. Will strike this medium, will get refracted from here, strike this medium, will get refracted from here, and it will finally emerge out of the medium, 6th medium, like this. Okay. In the question you are asked to find the angle of refraction of medium 4. So this, you are asked to find this angle. It's very simple. You know that Snell's law states that mu, the absolute refractive index of any medium, into sine of the angle which the ray makes with the normal, is constant for a particular reflection or for a particular refraction. Sorry. So for this refraction, I can write mu1 sine theta 1 is equal to mu2 sine theta 2. Now, since this surface is parallel to this surface, if this angle is theta 2, this angle is also theta 2, and this angle theta 2. For this refraction, now what happens? Mu2 sine theta 2 is equal to mu3 sine theta 3, because for this refraction, if I consider only this refraction, and if I apply Snell's law, I'll get mu2 sine theta 2 is equal to mu3 sine theta 3. Now this one I can write it as, now if I take this, I can write mu3 sine theta 3 is equal to mu4 sine theta 4. Similarly, if I take this medium, I can write is equal to mu5 sine theta 5 is equal to, I can write mu6 sine theta 6. This was one refraction, this was another refraction. Remember, I can write this because all are equal, because the surfaces are parallel. That's why this angle was equal to this angle. That's why this matched with this. Now from here, if I have to find theta 4, I can write mu1 sine theta 1 is equal to mu4 sine theta 4, or I can write theta 4 as equal to mu1 by mu4 sine theta 1, sine inverse of this. So this is my angle theta 4. Now, one more thing to note here is that, just have a look at this and this. Let's say that this medium mu1 and this medium, the first medium and the 6th medium are the same. Then what happens? Mu1 sine theta 1 is equal to mu6 sine theta 6. Mu1 is equal to mu6 because the two mediums are same. If the two mediums are same, what happens? These two are equal. That means theta 1 is equal to theta 6. Which means that if the initial medium and the final medium are same, the ray of light emerges parallel to the incident ray. So this ray emerged as parallel to this ray. Only what happens is there is a lateral shift. Here you have a lateral shift occurring. The ray has emerged parallel to the incident ray, but there is a lateral shift. Now let's find the lateral shift when we have one medium only. That means, let's say I keep a glass slab. Both of the two sides I have, let's say, air, and this width of the glass slab is W with a refractive index of mu. So as I said, the two mediums, initial and the final, are the same, and we have parallel surfaces. The two conditions are that the two mediums on both the sides should be same and the surfaces should be parallel. Then the rays will emerge parallelly. The emergent ray will be parallel to the incident ray, but there will be a lateral shift. So let's find the lateral shift. Okay, this is angle I, this is angle R. So what is this lateral shift? I need to find this, or I need to find this distance. What is this angle? This angle is I minus R. So if I assume this length to be x, I can write this displacement as what? This displacement is what? Let's say this displacement is d. D is equal to x sine I minus R. Now I need to find x. What is x? This width is w and this is x. This angle is R. I can write w by x as cos R or x as w by cos R. So my final lateral displacement comes out as w by cos R sin I minus R. So this is the lateral displacement which occurs in case when a glass slab is placed. There is only one medium in between and the two surfaces are parallel. So now we have moved into the concept, or we have introduced the concept of glass slabs. Now we'll discuss more about glass slabs in detail. Before that, I want to discuss something more. So now let's take this example. What we have here is a beaker where we have some liquid of refractive index mu. There's some point here at the bottom of the surface. Refraction occurs at this place and the refracted ray, my eye is here. So the question is, I want to know what is the depth at which this point appears to me. Remember, when we have a bucket full of water and this is the surface of the bucket, we have water here. When we look at the bucket, you might have observed that the surface of the bucket looks somewhat raised up. So if the surface is here, to me the surface may appear to be here. Why does this occur? This occurs because of refraction, and we'll learn this now. This is what we'll discuss now. So let's say that this point is here. So I want to know that if the real depth of the point is, let's dr, then what's the apparent depth which I see? Why does the surface or this point looks raised up? This is because of this. You see that if I take two rays which are necessary to find the location of the image, one of this ray is this normal ray, then the other ray is this one. So find the location of the image, I need to extend this ray. This ray, when extended, meets this point as this. So this is the location of this point, or the image of this point. So that's why my image is here. So that's why the point looks raised up, or the apparent depth is less than the real depth. Now let's draw a formula which relates the apparent depth dA with the real depth dr. Here we assume, or you assume, that we have a near normal observation, which means that my eye is somewhere very close to the normal, in which case I can write that sine of theta is equal to tan of theta. Let's assume this and let's find a relation between dA and dr. If we don't assume this, then also we can find a relation, and obviously that relation will be more complicated one. To simplify things, now let's assume that we have a near normal observation, and let's find the relation between dA and dr, where dA is the apparent depth and dr is the real depth. If I take this large triangle, this one, what can I write? If I take this large triangle, I can write, let's say this distance is x, this small distance, x by dr as tan of this angle is I, so this angle is also I. So tan of angle I